Welcome to this deep dive into data envelopment analysis or DEA. In a world obsessed with performance, efficiency isn't just a buzzword, it's a crucial metric for survival. But how do you accurately measure the efficiency of a diverse set of units, each using multiple resources to produce multiple outcomes? Traditional ratio analysis often falls short. DEA provides a powerful non-parametric linear programming based methodology to tackle this challenge. Today, we will explore the foundation of DEA, define its key players, and introduce the three most crucial models CCR, BCC, and SVM. So, what exactly data envelopment analysis is? DEA is a non-parametric mathematical method in operation research and economics. Its primary goal is to evaluate the relative efficiency of a set of homogeneous units. Instead of assuming a pre-specified functional form of the relationship between inputs and outputs as a parametric method like stochastic frontier analysis, the DEA uses the data itself to construct an empirical best practice production frontier. Imagine plotting all the entities being analyzed, the most efficient unit from a boundary or envelope around the data points. This boundary is the efficiency frontier. Every unit is then measured relative to the best practice frontier. A DMU that sits on the frontier is considered 100% efficient relative to the sample. A unit that lies below the frontier is considered inefficient, and DEA quantifies this inefficiency. It tells us for an inefficient unit how much its input could be reduced or its output increased to become a peer of the most efficient units. DEA's popularity stems for its ability to handle multiple inputs and multiple outputs simultaneously without requiring weights to be assigned a priori. Weights are determined through the optimization process itself, designing to make each unit look as efficient as possible. Central to DEA is the concept of the decision-making unit or DM. DMUs are the entities being evaluated, the fundamental units whose relative performance is being assessed. The choice of DMU is crucial as they must be homogeneous, meaning they should be performing the same basic task, using the same type of input and producing the same type of outputs. For example, in healthcare, DMU could be individual hospital, clinic, or departmental within a hospital. In banking, a DMU might be different branch offices. In education, there could be universities, public school, or specific academic programs. In manufacturing, DMUs might be various production plant. A DMU takes a set of inputs, the resources consumed, and transfers them into a set of outputs, the goods, services, or outcomes produced. Input could include labor hours, capital material cost, or square footage. Outputs could include unit produced, revenue generated, quality rating, or the number of graduates. The ratio of weighted outputs to the weighted inputs yields the efficiency score. Selection of the right DMUs, inputs, and outputs is the most crucial non-mathematical step in any DEA study. Now let's turn our attention to the foundation of DEA models, starting with the first and most widely used, the CCR model. The CCR model is named after the creators Chance, Cooper, and Rhodes, who introduced it in 1978. The CCR model operates under the assumption of content returns to scale. This means that if you double all inputs, you expect to exactly double all outputs. The scale of the operation does not influence its efficiency score. Efficiency, it means overall technical efficiency, which is a combination of both pure technical efficiency and scale efficiency. The ratio form. The basic idea in it is the ratio form is to maximize the ratio of weighted output to weighted input for a specific DMU, subject to the constraint that no other DMUs can have an efficiency score greater than 1 using the same weights. Mathematically, for any DMU K, the models seeks to find the weighted small ur for output and small vi for input that maximize its efficiency score theta k. Maximum theta k equal to summation r equal to 1 to s small ur yrk divided by summation I equal to 1 to m small vi xik, subject to the condition that the efficiency for all DMUs must be less than or equal to 1. Since this is a fractional program, it is typically converted into a linear programming problem for solving, often referred as the envelopment form or multiplier form. The CCR model is the benchmark. If a unit is CCR efficient, it means it is utilizing its resources optimally and it is operating at the optimal scale size. While CCR is powerful, the assumption of constant return to scale may not hold true in many real-world applications, especially when factors like size and regularity constraints prevent the DMU from operating at an optimal scale. This led to the development of BCC model. The BCC model, creator introduced by Banker, Chance and Cooper in 1984. Core assumption: the BCC model accounts for variable return to scale. This is achieved by adding a convexity constants to their programming formulation of the CCR model. The VRS frontier. The BCC model envelopes the data points with a more flexible, piecewise linear and convex frontier rather than a single ray from the region. This allows the efficiency score to reflect only pure technical efficiency independent of the scale of operation. Interpretation: a BCC efficient DMU is technically efficient, but it might not be operating at the optimal size. If a DMU is CCR inefficient but BCC efficient, it means its inefficiency is due to scale inefficiency. It's simply too big or too small. The BCC model provides a more realistic measure of managerial performance, as managers often have less control over the scale of the operation than they do over the technical efficiency of converting inputs to outputs. Both CCR and BCC are considered two radial models. They measure efficiency by finding the maximum proportional reduction in all inputs or proportional increases in all outputs need to reach the frontier. However, this is only valid if all inputs and outputs can be changed proportionally. What if some inputs are disproportionately wasted? This is where the slack-based measure or SBM becomes essential. The SBM model, proposed by Caro in 2001, non-radial approach. The SBM is a non-radial model. Instead of relying on proportionality adjustment, it directly incorporates slacks, the excess inputs or shortfall outputs into the efficiency score calculation. The SBM score is a function of the total slacks. It is defined as a ratio where the numerator reflects the total input excess and the denominator reflects the total output shortfall. The goal is to maximize these slacks relative to the current input and output levels. Advantages: directly deals with slacks. It provides a more accurate measure of inefficiency by accounting for non-proportionally improvement, unit invariance and monotonicity. Its efficiency score is unit invariant and is a monotone decreasing function of input and output slacks. The SBM model results in an efficiency score between 0 and 1, where 1 indicates an SBM efficient DMU with no slack. It's often preferred in application where the non-proportionality nature of inputs and outputs is a concern, offering a complete picture of inefficiency. Conclusion: to summarize, the data envelopment analysis is an invaluable tool for benchmarking and performance evaluation across diverse sectors. It empowers decision makers to identify best practice and pinpoint specific area of improvement. DEA, that is, it is a non-parametric method for constructing an efficiency frontier. DMUs, the homogeneous unit being evaluated. CCR, that is constant return scale, measure overall the technical efficiency assuming constant return to scale. BCC, that is variable return to scale, measure pure technical efficiency, allowing for variable return to scale. SPM, a non-radial model that directly addresses input excess and output shortfalls, providing a complete picture of slack-based inefficiency. Understanding this model is the first step. Thank you for joining us.